All right, 3.5, modeling with non-linear regression. Usually it has a thing. Oh, there it is. Okay. I was just double checking that I was presenting. Okay. Modeling with nonlinear regression. So your calculator, one of the most powerful things your calculator can do is to create mathematical models. You've done linear regression in Algebra 1. In this class, you've already done quadratic and cubic regression and an exponential regression. So you remember when we took the golden cat's body weights and their lengths in centimeters, and we created an exponential model or a power regression. So anyway, you've done some modeling. Now we're going to create some mathematical models, but we've got some one new model to consider, and it is the logistical growth function. So it's on page 202 in your text. I would note that location. It's the only one you haven't seen before, the logistical growth model. And it's when you have two horizontal asymptotes and the function goes between them. And it's really good for modeling population growths, because populations are always going to fall between 0 and the carrying capacity of the environment, which is often inhibited by food sources or predation, or a lot of things can impact the survival of a species. But if the population is healthy, it will approach the carrying capacity and ride that asymptote onto infinity. Always some catastrophic thing occurs, makes the population dip. But in an ideal situation, a population would follow the logistic growth function. And it's parameter C divided by 1 plus A times E to the negative BT, where E is Euler's number, C, A, and B are parameters that are greater than 0, and C is that carrying capacity value. And then to linearize, this is something I'll show you at the very end. It's a way to make nonlinear data appear to be linear. So if you want to take data that is in some nonlinear form and create a linear graph by rescaling or re-indexing the data, that is called linearization. Sometimes you'll want to do that because linear data makes more sense to people. When you look at a graph and see a straight line, it's just easier to interpret. All right. So let's do our first one of these. This is and this is almost purely calculator, so go ahead and take your calculators out. The growth of a culture of bacteria is shown in the table. Use exponential regression to model the data, and then use your model to predict how much bacteria there will be after 24 hours. So, first of all, stat, edit, clear out whatever data you have from an old problem. Don't use the delete button, use the clear button. The delete button causes a problem. And then we're going to put the X values in. Then we're going to put the Y values in. Notice there should be the same amount in L1 as there is in L2. Once you got that data in, you're going to hit Stat, Calculate, navigate down to EXPREG because they want an exponential regression. That gives us this, so that's our exponential model. Predicted after 24 hours. Well, there's a way to auto-populate. Question, Allie? Yeah. Just help me remember to get it back from you at the end of class.
Okay. Did you say to go to Stat and then Calculate and then?
Stat, Calculate, EXPREG.
Okay.
Is the you're welcome. Exponential regression. So once we have found this exponential regression, you have to do this step. You can auto-populate y equals with that regression by using the following button presses: VARS, Statistics, EQ, and REGEQ. So that auto-populates the y equals with the last regression equation found. If I now go to my table, I can go down to 24. And I see there's about 25,519 bacteria I should expect. And the number is a little different here because I used it, I rounded to the nearest hundredth when I did it this way long ago. Here it's more exact because I didn't round. So 25,519 is a better answer.
Can you go over one more time how to put that into the Y1?
Sure. It's a tricky step. All right, so to populate the last regression equation found into your Y1, hit VARS, option 5, statistics, navigate to the EQ tab, and then it's the first selection in that EQ tab. And of course, it's going to be off the scale here because the data is a lot bigger than -10 to 10. You have to modify your window if you want to see the graph. So I'd have to go from 0 to 25, and then from 0 to like 40,000. This is another way to find the value at 24. So if I trace and then hit 24, it tells me 25,519. All right, so that's exponential regression. Now let's talk about logarithmic regression. So a group of students studied a photograph for 30 seconds. Beginning one day later, a test was given each day to test their memory of the photograph. The average score for each day is shown in the table. Use logarithmic regression to model the data. Use your model to predict the average test score after 2 weeks. So that would be 14 days. Once again, stat, edit, clear out the old data. And we're 1, 2, 3, 4, 6, 7, 72.3, 69.8, 64.2, 62.9, 61.3, 60.5, 58.3. All right, so got the data in there. Now we go to stat, calculate, and LNREG, not LINREG. This is a linear regression. We want LNREG, the logarithmic regression. All right, so now that's the last one found. So we go to y equals, clear this out. VARS, statistics, EQ, and REG EQ. Populates the y equals with the last regression equation found. Once again, we can go to our table. That keeps us from having to worry about setting our window up. We need to go to 14. And it says about 53.8. Again, I probably approximated in my old answer here. No, I didn't. 53.8. Okay, any questions about exponential or logarithmic regression? A lot of button presses. You'll have to practice it, of course, which I'll give you a couple problems to do that with. But one of the most powerful things your calculator can do is model data. Okay, example 3 is about logistical regression. Now, logistical regression is far more mathematically complex than the other two regression operations. So complex, it often crashes your calculator. So if this happens, it's no big deal. Just restart the calculator and you should be okay. You might get something called memory overflow. I set this one up where it's unlikely to do it. So I had to use other than the book's example because the book's example crashed the calculator every time. All right, let's populate. This is about fish population. So we're releasing fish into a body of water, and then we're estimating the population density over a period of 2 years, 24 months. So put the months data in 0, 4, 8, 12, 16, 20, 24. And then the fish data, 125, 580, 2200, 5300, 7540, 8280, and 8450. So if I go to stat and then calculate, the one I'm looking for now is just logistic, option B here. And he's gonna think about this for a minute, because again, this challenges the software on your, or the hardware rather, on your little calculator. Nothing's wrong, it just actually takes that long. All right, so here's our model. If we go to y equals, clear this out, stat, calculate, VARS, statistics, EQ, and then REGEQ. So let's set our window up to go from 0 to 25, that's fine. And 0 to, looks like 10,000 would be a good number. And we see the logistical growth model of the fish population as it approaches the carrying capacity. So there was no specific task here other than to find the logistical growth model. All right, questions about anything? Oh, excuse me. All right. So choosing a regression. So what you want to do is make a scatter plot of the data and then see which one of these shapes fits it best. So that is how you choose a model. Look at the scatter plot of the data and determine which of these shapes is most appropriate for that data.
Can we sketch all these down?
I would. Yeah, I think this is worth knowing. I don't like my drawing of logarithmic here. I don't know what I was thinking. It should be more clear that it has a couple horizontal asymptotes. No, wait a minute. This is logistic. Yeah, so never mind. It was right the way it was. I mixed up logarithmic and logistic. Yeah, these don't have to be Mona Lisa works of art. Just a quick sketch. And some of these are a pretty subtle difference. The right side of that quadratic and then the power function, for example, difficult to tell apart. Exponential in the power, very similar shape. Exponential is just a little steeper. So basically, make a scatter plot and then you determine which of these shapes it most appears to be. There usually is one best answer, but any model will work to one degree or another. Usually one of these will work best, but the second best one will work like 95% is good. So sometimes it's difficult to make that distinction. You've probably used the first 4 pretty frequently. The last 2 are probably the newer ones for you. All right, let's move on. So use the data in the table to determine the best regression equation. So let's look at, so this is profit from a a side business this person has. We're going to edit the data, stat edit, clear out the old stuff. Put in 1, 2, 3, 4, 5, 6, and then 1780, 3168.40, 5369.75, 10038.76, 17868.99, 31806.80. Okay, again, this is intended to model profit from an internet company. And we want to know, when should we expect them to make 100,000? So that's our task. We're going to use a model to predict that. Let's go to y equals, clear out this old regression data, hit enter on the plot 1. That'll turn plot 1 on. And then for our window, 0 to 25 is okay. And we want to know when it hits 100,000. So we'll need 100,000 worth of y. So there's my data. And which of these shapes is that most like? I'm thinking power regression. But exponential would not be a terrible choice. Quadratic would not be a terrible choice. But I'm thinking power function. So we'll just see how that goes. If I hit quit to the home screen, stat, calculate, and then go down to power regression, and then go to y equals, bars, statistics, EQ, reg EQ, and I'm going to graph the, that's not great, is it? So let's try exponential instead. You see how this is not quite steep enough? Quit to the home screen, stat, calculate, EXP-REG this time. Y equals, clear this out, VARS, statistics, EQ, REG EQ, graph. Much better. So exponential was the better of the two choices I thought about, and clearly this is good. Now, when is it going to hit 100,000? That's a million. Yeah, there we go. And I'll change my window to go up to 110,000 so I can see that line more clearly. So this intersection is what I'm concerned about. Use the intersect function. You don't want, y1 is my first, and then y2. Don't let it select the plot. About 8 years. We should expect it, according to my model. Okay, so linearizing data. This graph is in your text. You're going to have a question about linearization, and there are 4 scenarios here. So don't bother to write all this down. Just note its location in your text, which I should have that page on here already. 204. Yep, there it is. So page 204. So there are 4 ways we can linearize data, and it depends on what the shape of the original function is, what kind of data we're dealing with. So you change the x's and y's, in some cases just the y, in some cases just the x, and in the last case both the x and the y. But you'll change them as you see here, and that will be the linearized data. So a quick example of that. So make a scatter plot of the data, linearize, assuming a power model. So for a power function, you remember what we just looked at from page 204, it says graph ln x and ln y. So that means we take the natural log of all of these x's, the natural log of all of these y's, and we're going to find the linear regression. All right, so let me show you how that would work. Stat, edit, clear out the old data. And instead of just the 0.5, because this asks us to take the natural log of the data, I'm going to put in ln of 0.5, ln of 1, ln of 1.5, ln of 2, ln of 2.5, ln of 3, ln of 3.5. This is kind of tedious. Ln of 4. And then for the y's, ln of 0.38, ln of 3, ln of 10.1, ln of 24, ln of 46.9, ln of 81, ln of 128.6, almost there, bros, ln of 192. Make sure the number of data entries match. Quit to the home screen. Stat, calculate. This time we are going to do LINREG. So y equals, leave the plot on, clear this crap out from the previous problem. Vars, statistics, EQ, REG, change our window to go from 0 to ln of 4. Well, let's just put like 5. That'll be plenty of x. And then 0, ln of 192. I don't know, like 20. There we go. Good deal. All right.
So what did you go to stat calc? Like what option was it?
LINREG. So for linearized data, use linreg, LINREG. All right. And that, ladies and gentlemen, is chapter 3, part 5. Let me close my meeting here.